There's a machine in your pocket right now doing something that sounds impossible. It's writing with a tiny metal ball that has to spin thousands of times a second without ever falling out or drying up. And by the end of this, I'll show you the one bent piece of wire that makes it work. But first, 9 other everyday things hiding genuinely brilliant engineering, counting down to the one that honestly threw me. We'll start gentle. A zipper looks like teeth just mashing together. They're not. Each tooth has a tiny hook on top and a hollow on the bottom, and the slider is a Y-shaped wedge that forces them to interlock at a precise angle, one pair at a time. Here's the bit nobody points out: the teeth don't actually touch the tooth opposite them. Each one grabs the tooth diagonally above and below on the other side. That's why a zip holds under load but slides so easily. Whitcomb Judson patented it in 1893 and it barely worked. The version you used took another 20 years. Speaking of things that took decades to get right, the ballpoint pen. That little ball is usually tungsten carbide, about 1 millimeter across, sitting in a socket with a clearance of just a few microns. As you write, the ball rolls, picking up ink from a reservoir behind it and laying it on the page. It's basically a rolling stamp. The genius is the ink. It's a thick, oily paste, not runny like a fountain pen. It only flows when the ball's rotation drags it out, and it dries the instant it hits paper. That's why it doesn't leak in your pocket but writes the second you press down. Laszlo Biro cracked that ink formula in the 1930s. Now here's one you touch constantly and never think about. Every key you press bounces. When the metal contacts inside a switch touch, they don't close cleanly, they physically chatter, opening and closing dozens of times in a few milliseconds. Left alone, one press would type 10 letters. So there's a trick called debouncing. The chip waits a few milliseconds, ignores the chatter, and only registers the key once it's settled. That delay is baked into every keyboard on Earth and you've never felt it. Mechanical keyboards use a spring and stem you can hear. Membrane keyboards use a spring and stem you can hear. Membrane keyboards squash a rubber dome onto a printed circuit. Either way, software is quietly cleaning up a mess 100 times a second. An induction hob has no hot element. The glass surface stays cool. Underneath is a coil carrying alternating current at around 20 to 50 kHz. That creates a rapidly flipping magnetic field. And when you put an iron or steel pan on top, the field induces swirling electrical currents inside the pan's base, eddy currents. The pan's own resistance turns those into heat. The pan is the heater. That's why it only works with magnetic cookware and why it's so fast. You're depositing energy directly into the metal, not warming a coil and hoping. Honestly, the first time I understood this, it felt like a magic trick. Now, keeping time without a battery. A mechanical watch has no electronics, yet keeps time to seconds a day. The secret is the escapement, a toothed wheel and a rocking lever that releases the gear train one tiny step at a time, giving that tick-tick sound. It's regulated by a balance wheel swinging back and forth on a hairspring, usually 5 times a second. Every swing lets exactly one tooth escape. So the mainspring's raw force gets chopped into perfectly even pulses. Thomas Mudge perfected the lever version around 1755, and we still use it today. Millions of parts, all governed by one spring, the width of a hair. Speaking of springs doing invisible work, a retractable pen. Click, out, click, in. Inside is one of the cleverest little mechanisms in your desk drawer. There's a cam body with slanted teeth, a plunger, and a rotating collar. Every time you press, the collar rotates a fixed angle and its teeth land in a deep slot or a shallow one, alternating between locked out and locked in. It's a rotary ratchet that turns a straight push into a twist. Watch a transparent one in slow motion and you can see the collar spinning a few degrees per click. It's the same logic as a retractable tape measure lock. Genuinely elegant for something we throw away. Next, food heated from the inside out. A microwave doesn't add heat, it shakes molecules. The magnetron produces waves at 245 GHz, and water molecules are polar, meaning one end is slightly positive, the other negative. The field flips direction 2.5 billion times a second, so the molecules flip with it, jostling their neighbors, and that friction is heat. Here's the part nobody mentions. Those waves form standing wave patterns with hot and cold spots. That's the whole reason the turntable exists, to drag your food through them. No turntable, and you get a cold center and a scalding edge. Every reheated meal is molecular vibration. Now, 2 objects that hold impossible loads. A pin tumbler lock is beautiful. Inside are pairs of spring-loaded pins, a key pin and a driver pin, sitting across a gap called the shear line. With no key, the driver pins bridge that line and jam the cylinder solid. The right key pushes each pin stack up so every gap lines up exactly at the shear line and the plug turns. What amazes me is the tolerance. We're talking fractions of a millimeter per pin, 5 or 6 pins deep, and it's essentially unchanged since Linus Yale Jr. patented it in 1861. Lockpickers exploit tiny manufacturing errors to set 1 pin at a time, down to the top 2 now. A sewing machine baffled people for decades because you can't push a needle all the way through fabric and back. The thread would just pull out, so they cheated. The needle only dips through, carrying a top thread, and forms a little loop underneath. A rotating hook spinning below the plate catches that loop and wraps it around a second thread from the bobbin. Pull tight, and the 2 threads lock together in the middle of the fabric, a lock stitch. It happens hundreds of times a minute. Elias Howe patented the 2-thread idea in 1846, and it changed manufacturing forever. 2 threads that never actually pass through each other, yet lock solid, and number 1 still tops it. Here it is, and it's absurdly humble. The safety pin. One single piece of